Welcome back to the deep dive. Today, we are really going deep, like way beneath the surface of artificial intelligence. We're not talking about the flashy new models, not yet, anyway. We're looking at the absolute bedrock, the foundations.
Yeah, the mathematical steel and concrete, you could say.
Exactly. If AI is this huge skyscraper, we're digging down to see what actually holds it all up.
That's right. And our mission today is, well, pretty straightforward. We're diving into the mathematical language that underpins almost all of machine learning.
Which is linear algebra.
Primarily, yes. We'll show you how these core tools get applied immediately in supervised learning, things like regression and classification.
Okay.
Ultimately, we want you, the listener, to understand this mathematical toolbox that lets computers juggle, well, massive groups of numbers all at once.
So we'll unpack the structures, vectors, matrices, and then look at the rules for combining them.
Exactly. And then show how that math translates directly into a core AI task.
Yeah.
Finding that best fit line or curve in your data.
Got it. Let's dig in. Okay, so this toolbox, linear algebra. It's basically the infrastructure, right? Turning raw data into these organized blocks we can actually work with.
That's a great way to put it. It gives us structures, vectors, matrices, tensors, and then the rules for adding, subtracting, multiplying them.
Let's start with the basics then. Vectors.
Right. So a vector, simplest form, it's just a list of numbers, a 1D array.
Like tracking someone's age, height, weight.
Exactly. Those three numbers. That's a vector. Geometrically, it's helpful to think of it as having both magnitude, how far, and direction, which way, like an arrow pointing from one point to another potential point.
And you mentioned a unit vector.
Yes.
Yeah.
That's just a special case where the magnitude, the length of that arrow is exactly one. Very useful for representing pure direction.
Okay. So what happens when we need more than just one list? When do we need a matrix?
Well, if you have lots of vectors representing, say, lots of people's data, you stack them up. That's a matrix.
So our age, height, weight example, but for 100 people?
Exactly.
Yeah.
That whole data set becomes a matrix, usually n rows by m columns. And critically, matrices aren't just for storage. They represent transformations.
Transformations, like changing the data somehow.
Precisely. If you want to rotate an object in 3D space or scale an image up or down, you multiply its data, maybe it represented as vectors, by a specific transformation matrix.
And if n equals m, rows equal columns, that's a square matrix.
Correct. Square matrices have some special properties we'll likely get into.
And bigger still, tensors.
Tensors are the ultimate generalization. They're multidimensional arrays.
So a vector is 1D.
A 1D tensor.
A matrix is 2D.
A 2D tensor.
And tensors can be 3D, 4D, whatever.
Exactly. Think about color video data. You've got height, width, color channels, and time. That's inherently more than 2 dimensions. You need a tensor for that. It's absolutely critical in deep learning.
Okay, structures make sense, but we need rules to combine them. Let's talk dot product. Takes two vectors, gives one number, a scalar. Why is that calculation so important?
Because the dot product is fundamentally how a machine applies weights or measures similarity.
Weights.
Yeah.
Right.
Imagine you have one vector with house features, size, age, location, and another vector with how important each feature is the weights. The dot product instantly calculates the overall weighted score for that house.
Ah, okay, so it's like a core calculation.
It's the core calculation in basically every layer of a neural network. It's everywhere.
I remember reading something surprising. If two vectors are perpendicular, their dot product is 0. What's the intuition there?
It means they're completely independent, directionally speaking. One points in a way that has no component along the other's direction. In high-dimensional data, if that dot product is 0, it tells you feature A gives you absolutely no information about feature B along that specific axis. They're orthogonal.
Interesting. Okay, rules get trickier for matrix multiplication.
They do. There's one really strict rule you absolutely cannot break.
Which is?
The number of columns in the first matrix must match the number of rows in the second matrix.
Why is that so strict?
It's not arbitrary. It falls out of the definition.
Yeah.
You're essentially doing a series of dot products. For each row in the first matrix, you take the dot product with each column in the second matrix. If the lengths don't match columns in the first, rows in the second, you just can't do the dot product.
Okay, the dimensions have to line up for the dot products to work. Makes sense.
And the resulting matrix has the number of rows from the first matrix and the number of columns from the second.
Got it. What about those special matrices, like the identity matrix? You said it's like multiplying by 1. Why do we need that?
Well, remember, matrices often represent transformations. The identity matrix, usually written as $, is the do-nothing transformation. If you multiply any matrix or vector, by $0, you get the exact same thing back.
A baseline.
Exactly, a baseline of no change. It's crucial for solving equations.
Which brings us to the inverse matrix, M1 the undo button.
Sort of, yeah. If you multiply a matrix dollars by its inverse M1, you get the identity matrix M1.
1M1.
Correct. This is how we effectively divide in the world of matrices. It's key for solving systems of linear equations.
There's a catch, right? Not every matrix has an inverse.
The huge catch. Two main conditions. First, the matrix must be square. Second, and this is critical, its determinant cannot be 0.
Wait, the determinant, if that's 0, the whole thing breaks. What does that mean practically?
It means the matrix is singular. Think of it this way. The transformation represented by that matrix squashes the space down into fewer dimensions, like collapsing a 3D object onto a flat 2D plane.
You lose information.
Precisely. You've lost a dimension of information, and you can't reliably undo that collapse. If your data leads to a matrix with a 0 determinant during model training, the system often becomes unsolvable. There's either no unique solution or infinite solutions, and the algorithm usually just stops, crashes.
Okay, wow. That's a fundamental failure point then.
Absolutely.
All right, one more math tool before we apply it. Eigenvalues and eigenvectors. What's special here?
This is super insightful for understanding data. An eigenvector is a special vector whose direction isn't fundamentally changed when you multiply it by $.
It just gets stretched or shrunk?
Exactly. It only gets scaled by a factor, and that factor is the eigenvalue, lambda AR. Most vectors get pointed in a completely new direction when multiplied by a matrix, but eigenvectors just scale along their original direction.
Why is that important for AI?
Because eigenvectors point along the principal axes of the transformation represented by the matrix. They show you the stable directions, the directions where the data stretches or compresses the most, or at least. This is the core math behind techniques like principal component analysis, or PCA.
PCA for dimensionality reduction.
Yes. If you have data with hundreds of features, the eigenvectors corresponding to the largest eigenvalues tell you which combinations of features capture the most variance, the most information. You can often keep just a few of these principal components and discard the rest, drastically simplifying your data without losing the crucial patterns. Eigenvalues tell you how much variance each eigenvector captures.
Phew, okay. That was quite the toolbox tour. Vectors, matrices, dot products, inverses, eigenvectors. I see the algebra part now. So we have these structures to hold data, rules to combine them, ways to find key directions. How does this all start learning things?
Right. This takes us straight into supervised learning. The key word is supervised. We start with a data set where we already have the right answers.
Labeled data.
Exactly. We have input samples, let's call them 6JO, and for each one, we know the correct output, GuiJ. These 6J$ are our features, or independent variables. The JD$ are the responses, the dependent variables.
And the goal is?
The goal is for the computer to figure out some function, let's call it VES, usually of a fairly simple form, like a polynomial or something, such that when you feed it an input 6J, the function's output, fixj, is really, really close to the actual known answer data.
Trying to map inputs to the known outputs.
Precisely.
And usually in supervised learning, we're tackling one of two main kinds of problems.
That's right. The first is regression.
Predicting a number.
Yeah, predicting a continuous or quantitative value, like predicting house prices, tomorrow's temperature, someone's exact weight. The output can be any number within a range.
And the second?
Classification. Here we're predicting a discrete category or a qualitative label.
Like spam or not spam.
Perfect example.
Yeah.
Or identifying an image. Is it a cat, a dog, or a bird? You're assigning the input to one of a predefined set of classes.
Okay, regression for numbers, classification for categories. But regardless of the goal, the actual learning process seems to follow a cycle. You mentioned 3 steps.
Yes, this cycle is fundamental to how most machine learning models are trained. Step 1, representation.
Choosing the type of function.
Essentially, yes. What's the formal language? The set of possible functions or hypotheses the computer can even consider? Are we looking for a straight line, a parabola, a decision tree, a neural network? You have to define the space of possibilities.
Okay, step 1, choose the model type. Step 2.
Evaluation. How do we judge success? We need an objective function, or more commonly, a loss function.
This measures how bad the predictions are.
Exactly. It quantifies the error. How far off was fxj$ from the true yj$? Lower loss is better.
Makes sense. And step 3.
Optimization. This is the search algorithm. Given the chosen representation and the evaluation function, the loss. How do we efficiently search through all the possible functions in our chosen space to find the one that has the absolute minimum loss?
Find the best function according to our error metric.
That's the loop. Represent, evaluate, optimize.
Let's make this concrete. Focus on the simplest case, linear regression. Our representation is super simple. Just a straight line, y to y equals plus b.
Right.
We have a cloud of data points, xj, yj, doll. Our job is to find the specific slope, axure, and the specific intercept that make that line fit the cloud of points as well as possible.
And we need to define as well as possible mathematically. That's the evaluation step. How do we measure the error?
The distance from the points to the line.
Yes, specifically the vertical distance. For each point xj, yj, the line predicts a value xj plus b. The error for that point is the difference, xj plus b.
But some errors will be positive, some negative. They'd cancel out if we just sum them.
Exactly. So the standard approach is to square each error before summing them up. This gets rid of the negative signs and penalizes larger errors more heavily.
Ah, the sum of square errors, SSS.
Easily. Our loss function, let's call it dollars, is now LABB ma yj xj b22. This function MUP depends only on our unknown parameters a and bevel.
So the goal of optimization is now find the values of 7 that make this sum lollers as small as possible, like finding the bottom of a valley.
Perfect analogy. The loss function LIB defines a surface, potentially like a bowl. We need to find the coordinates at the very bottom of that bowl.
And how do we find the bottom? That's where calculus comes in, right?
Yes, specifically partial derivatives. At the absolute minimum point of any smooth function, the bottom of the valley, the slope must be 0 in all directions.
Flat.
Flat. So we need the slope of the loss function Lawler with respect to changes in AGs to be 0, and d the slope with respect to changes in the LAR to be 0. So we calculate those partial derivatives, and then we set both of them equal to 0.
Frac partial A and frac partial B.
That gives us a system of 2 linear equations with 2 unknowns, A and ball.
And we can solve that system using linear algebra.
Exactly. And because we started with a linear model, x plus b per I, and used the sum of squares loss, this system has a nice clean solution. We can derive formulas for algebra directly, often involving the means of the 6 and yin values.
A closed form solution. No need for guessing or iterating.
For simple linear regression, yes, the math gives you the exact answer directly. It's quite elegant.
But what if the data clearly isn't a straight line? If we need a curve, say polynomial regression, we generalize a lilacs plus b ball to something like all x plus thus theta 1x plus dots plus theta x k, a polynomial of degree egaler. Does finding all those theta parameters make the optimization much harder?
Here's the really neat part, a key insight. Even though the function do nonlinear and the input variable 6-Taylor gets curvy, the loss function is still based on the sum of squares, vel and I, hj.
Okay.
And if you look at how the parameters vat, theta appear inside that sum, the loss function dollar is actually still a quadratic function of those parameters.
So finding the minimum still involves setting partial derivatives to 0.
Yes. You calculate partial theta dollars for each parameter. And what you get is still a system of linear equations in the unknown parameters. Theta 1, dots.
Wow. So even though the fit looks like a complex curve, the process of finding the best parameters is still fundamentally solving a system of linear equations.
Exactly. The structure of the optimization problem remains linear in the parameters. That's incredibly powerful. It means we can use the same linear algebra machinery to solve for the coefficients of these complex curves, as we did for the simple straight line.
Okay, so we've built this powerful machinery. We can take data, choose a model type, linear polynomial, define a loss function like SSE, and use calculus and linear algebra to find the parameters that minimize that loss on the data we have. Seems like we've solved it.
But here comes the crucial test. Minimizing loss on the training data, the data we use to find the parameters, is only half the battle.
Right, the real goal is generalization.
Precisely. Does the model perform well on new, unseen test data? Data it wasn't trained on. That's the only thing that truly matters in practice.
And why wouldn't it, if it learned the patterns well?
Because the training data is almost never perfect. It always contains noise.
Noise, like random errors.
Yeah, random errors, measurement inaccuracies, accidental quirks that just happen to be in that specific sample of data, but aren't part of the true underlying pattern. The huge challenge is that the learning machine doesn't automatically know the difference.
It just sees numbers. It doesn't know which patterns are real and which are just flukes in the training set.
Exactly. It tries to fit everything, including the noise.
And this leads to the infamous problem of overfitting.
Yes. Imagine you have data that roughly follows a simple sine wave, but with some random jitter added to each point.
Okay.
Now, you decide to fit it with a really complex model, say a polynomial of degree 9.
That's a very wiggly line.
Extremely wiggly. And that polynomial has enough flexibility to bend and twist and contort itself to pass exactly through almost every single training data point, noise and all.
So the loss in the training data would be incredibly low, near zero maybe?
It would look like a perfect fit on the training data, but the polynomial hasn't learned the underlying sine wave at all.
It learned the noise.
It essentially memorized the noise specific to that training set. Then, when you show it new test data drawn from the same sine wave plus noise process,
It fails completely.
miserably,
Yeah.
because the specific noise pattern in the test set is different from the training set noise it memorized. The highly complex model that looked perfect is actually useless for generalization.
It's like studying only one old exam paper down to the tiniest detail, including the typos, and then being completely lost when the actual exam asks slightly different questions based on the same core principle.
That's a fantastic analogy. It learned the specifics, the quirks, not the general principle. Hashtag tag tag outro.
So wrapping up, we've journeyed from the basic structures of linear algebra vectors holding data, matrices transforming it, all the way to using calculus, those partial derivatives, as the engine to find the best fitting lines or curves by minimizing error.
We saw how these tools form the bedrock of supervised learning, especially for regression problems.
But we ended on this critical challenge. Just minimizing error on the training data isn't enough. It can lead straight to overfitting, where the model learns the noise instead of the signal.
Right, which really highlights that minimizing training error, while mathematically necessary, isn't always the best policy for building a useful model.
So that leaves a lingering question, doesn't it? Something for you, the listener, to think about.
Indeed. If just minimizing the straightforward loss function can trick the model into fitting noise, what's the next step? What other tools or principles, beyond just minimizing that simple sum of squares error, does AI need to use?
How does it learn to prefer simpler explanations, to distinguish the real signal from the random noise? What mathematical knobs can we turn to encourage generalization and avoid overfitting?
Yeah, that's a challenge, isn't it? Moving beyond pure optimization towards models that are also, in some sense, robust or perhaps elegant. That's a whole other layer of complexity.
A question for a future deep dive, perhaps. For now, thank you for joining us as we explored the mathematical toolbox of AI.